So we've learned our product and quotient rules. Today what I want to look at are the rest of the trig functions. Just realized this was open. Okay, the rest of the trig functions. Now, we could derive all of these, but we're not going to, okay? I'm going to derive tangent, just so you guys can see how this works. But cosecant, secant, cotangent could very easily be derived in similar ways. We're also going to, I have here the derivative of the exponential function. This is a nice one. The derivative of e to the x is e to the x. Okay? So, here you have all of your trig functions and e. And we can see here that the derivative of tangent is secant squared. Okay? It's secant squared. So let's see how we would get this. Okay? First of all, tangent is also equal to what? Yeah, sine over cosine. Sine x over cosine x. And this obviously now leads us, as we are looking for a derivative, to the quotient rule. Okay? So, the f, if you will, the numerator is sine, so the derivative of sine is cosine. Alright, so that's cosine. And the derivative of cosine is negative sine. So, I have the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared, cosine squared. By the way, there's a little way to remember this. It's low d high minus high d low over low squared. Low d high minus high d low over low squared. But the fraction kind of rolls off the tongue, you know? Here. This is high. Hang on. I should have mentioned this yesterday. This is high, this is low, right? Numerator, denominator. So, low d high minus high d low over low squared. Okay? If that makes no sense, forget I ever said it. Alright. But let's go ahead and simplify this, alright? What does our numerator come out to? Cosine squared x plus sine squared x. Ah, someone remembers their Pythagorean identity. Cosine squared plus sine squared, oh yeah.
Do I have to go back?
Cosine squared plus sine squared equals 1. This is 1 over cosine squared, which is? Secant squared. Okay?
Oh, can you not cross that out? I would cross that out.
Cross out what? Oh, no. Because you got addition here. You cannot cancel it out if it's addition. Now, if you split this into two separate fractions and made it cosine squared over cosine squared, that would be 1. But then you would have also a sine squared over a cosine squared, which is tangent squared, and what does 1 plus tangent squared equal? Secant squared, okay?
So that's proper.
You would have gotten there. Yeah, that's another Pythagorean identity.
I can't do it without dividing by.
Yeah. So now that we know those rules, we can now find derivatives of an increasing number of functions here. Okay, so we have the derivative of y equals x minus tangent of x. So dy dx is the derivative of x is 1 minus, what's the derivative of tangent? Secant squared. Okay? What's 1 minus secant squared?
minus sine anything? Sine squared? Or secant squared? It's one to two.
1 plus tangent squared is secant squared. So negative, there we go. Someone got the negative. Negative tangent squared.
Just these I heard of one, I'll say every other answer. So it's
Okay? Negative tangent squared. Okay? Okay, so then we have the derivative of y equals x times secant. So what are we going to have to use here? Product rule, okay? So the f prime here is 1. The g prime here is, what's the derivative of secant?
secant x times
Secant times tangent, yep. Okay, so our derivative, let me move this over a little bit, is f prime times g plus f times g prime. Okay, simplifying that a little bit, we can factor out a secant, and we get a 1 plus x tangent of x. All right. So it's the same stuff that we've been doing. It's just a little bit different simplifying because we got to remember our tangent, our trig identities.
Not simplify that further.
Can't really. I mean, you could make it all in terms of sine and cosine, but that's not going to help us. Okay.
you say you don't do it, and you say you don't need to memorize all the derivatives.
No, you do have to memorize all those derivatives.
Obviously, well, if we saw this on the exam, we wouldn't have time to derive them.
Yeah, if you're doing the AP exam and you're having to rederive all your rules, you're not going to finish. So, but here's the thing. That's like, what is that, 6-7 months from now? At that point, you'll have them memorized. You know, we're going to use them so much. It's actually 8 months from now. We're gonna use these so much, you'll have these memorized, no problem. Okay? So here we have example 3. We're gonna actually prove that the derivative of both of these is equal. Okay? Now, if I were to separate this left side into 2 separate fractions, I would get cosecant minus cotangent. And basically what we're doing here is we're proving that even if you have equivalent expressions, when you take the derivative, you'll get the same thing. Okay? So whether you leave it like this on the left, 1 minus cosine over sine, and you do the quotient rule and take the derivative, or whether you take the derivative of cosecant minus cotangent, you should end up with the same answer at the end. Okay? So let's go ahead and do both of these. We'll do the left-hand side in blue. All right, so we have the top is 1 minus cosine x. So what is f prime? What's the derivative of 1 minus cosine x?
Sine.
Sine x. Very good. Okay. Sine x.
Wait, what about the negative?
The negative, it's negative sign, so negative sign is positive sign. Okay? And then g is sine x. So f prime, or sorry, g prime
Cos x.
is cosine x. Good. So let's use our quotient rule now. Okay, dy dx. F prime g minus f g prime all over g squared. So f prime is sine times g is sine minus f, which is 1 minus cosine, times g prime, which is cosine,
Over.
all over
Sine squared.
Sine squared. The g squared. Okay? So sine squared minus cosine plus cosine squared over sine squared. Okay? So
Wait, you wrote sine squared. Do you mean sine squared x?
Yeah, sine squared. First one.
oh, yeah, here, x. Thank you.
I actually have a question.
So you have 1 minus cosine, is that it?
So yeah, the top, and guys, this is where this these identities come in handy. Sine squared plus cosine squared
Equals 1.
is just 1. So we have 1 minus cosine x
Then equals sine x.
Over sine.
over sine x.
Can we?
Sine squared x.
I was
Sine
doing
squared.
that.
Alright, so let's do the right hand side. And here we're going to need some of our new rules, okay? What is the derivative of cosecant x?
Negative cosecant x times cotangent.
Okay, good. The derivative of cosecant is a negative cosecant times cotangent. So then minus, what's the derivative of cotangent?
Negative cosecant x squared.
Yes, negative cosecant squared of x. Alright, so where can we go with this? That looks nothing like what the other side is.
Sure, we can like
You could
transform
break
them.
everything down into sines and cosines, so
Yeah.
you can simplify from there.
We can. We can.
Yeah.
Let's see what we can do with this. We got a negative, what's cosecant?
1 over sine.
1 over sine. Cotangent,
1 over tangent.
1 over 10.
1 over tangent, or
Cosine.
cosine over sine.
Yeah.
Oh, hey, I see I've got a sine squared in there, right?
Yeah.
Although
And then what do we have here?
cosecant squared.
Plus a cosecant squared. What's cosecant squared equal to?
1 over
Cosine squared over sine squared.
1 over
That's cotangent squared.
Cosecant. 1 over cosine. Sine squared.
1 over sine squared. Okay? 1 over sine squared. So, hey, it looks like we might be there, right?
Same denominator.
They have the same denominator. Now now we've got a sine squared here, right?
Yeah.
And we got a minus cosine x plus 1 over
sine squared.
sine squared x. Are those the same thing? Yep, it is.
Wait, how did you get the minus cosine x?
Because we had a negative 1 over sine, negative 1 over sine times cosine over sine. So I just pulled this negative up here with that. Okay? So guys, here we can see, even if the two functions are equivalent to begin with, then their derivatives will be equal.
Okay.
Okay? You might have to do some manipulating to get them to look equal, but they will be. Okay? Alright, so let's do example 4. Let's do this third part. We'll skip the first two because those are pretty simple. I think you guys are getting things well enough. We can skip those. Alright, it says to rewrite with a constant multiple. Remember the constant multiple, if you had, say, a 4x squared, you just take the derivative of x squared and then at the end multiply it by 4. So, if I'm taking the derivative, hey, please, okay? If I'm taking the derivative of this whole thing, negative 3 times 3x minus 2x squared all over 7x, I can see this as something times negative 3/7. Okay? Now I can only do this because it's multiplication. Alright? But I could rewrite this as a negative 3/7 times the derivative of 3x minus 2x squared all over x. You guys see that? Initially, you might say, well, I'm going to have to use the quotient rule. And you could. There's nothing wrong with that, but guys, the quotient rule is messy. If we can avoid using the quotient rule, let's do it, okay? In this case, because there's only a monomial in the bottom, when I rewrite it like this, I can continue to rewrite it by dividing, okay? What's 3x minus 2x squared divided by an x?
3 minus 2x.
Yeah, 3 minus 2x. You cancel out an x, the common factor of x in the numerator, and now, the derivative of 3 minus 2x, that's pretty easy. It's negative 2. So I have this negative 3/7 times a negative 2. So 6/7 is our derivative. Okay? 6/7 is the derivative. Okay? So there are cases where it may appear as though you need to use quotient rule, but especially cases like this where there's a monomial in the denominator, you often can get away with not having to. Okay? Let's talk about things like 5 and 6. Okay? 5 and 6. So looking at graphs of functions. Okay, so if I want a function where f is greater than 0, but f prime is less than 0 for all real numbers, let's pick out what this exactly means. What does it mean if f is greater than 0 for all real numbers? It's always above the horizontal axis. Okay? Always above the x-axis. But what does it mean if the f prime is always less than 0?
It's always going to be going down.
Yeah, it's always going to be decreasing. Now, how in the world can I always decrease but stay above the x-axis?
Approach 0.
All right, so 0 must be a what? A horizontal asymptote, okay? So, if I'm drawing a function...
But why isn't it the limit?
What?
Why are you saying it's a horizontal asymptote and not a limit?
Well, because it's got to be defined for all real numbers. But, I mean, remember the horizontal asymptote, the value that that's at is the limit of the function as x approaches infinity. Okay? Here's what my function might look like. Might look something like that, like an exponential decay function. Alright? Notice it's always above the x-axis. We've got an asymptote here at y equals 0 that it's going to approach but never reach. If I took the limit as x approached infinity,
It's 0.
then the limit would equal 0, yes. Okay? Okay? The last one here. Here are graphs of f, f prime, and f double prime. Which one is which?
F is the, what does it mean? Which? Oh, f is the parabola. F prime is the linear function, and f double prime is the line.
You guys think?
Well,
Yeah.
I know that F double prime's a line because the more you simplify it, the more basic the function gets.
Yeah.
Okay, yeah, this is polynomial, right? So we're losing a degree. So this is going to be something with an x squared. Then this has some kind of a linear function. And then this is just a constant. So the constant, that's going to be the f double prime. The line is f prime, and the parabola is f. Okay? Good job. Alright, so example 8, we want the second derivative. The second derivative. Now, what is the second derivative? Yeah, you take the derivative of the derivative. So the first thing that we have to do for, let's go ahead and do the first one here, is we have to get the derivative. Now, how am I going to get the derivative of this? Okay, if I brought the x to the top, how would I have to do it?
You would have to multiply by x.
By x to the negative 1.
Okay, I would have to rewrite it as x to the negative 1. Okay?
Can you just divide each term by x?
Or, yeah, split it up into separate fractions. However you guys choose to do that. X squared over x plus 2x over x minus 1 over x. So that's going to be x plus 2 minus x to the negative 1. Since I got to do the derivative, I'll go ahead and rewrite the negative exponent too. Alright? So that's kind of nice. So now I know that f prime equals what? 1. Derivative of 2 is 0. So, and then positive x to the negative 2. Very good. Okay? So there's our first derivative. Now we can get the second derivative. So we do f double prime. Derivative of 1 is 0. There you go. And at this point, I would go ahead and rewrite that as negative 2 over x cubed. Okay? So there's my second derivative. Number 8. Okay, let's skip down here to example 9. What are you given here?
Second derivative.
You're given the second derivative. What derivative do we want? The third derivative, okay? So, how many times do I have to differentiate? Just once, okay? So, f double prime, I'm going to rewrite as 2 minus 2x and negative 1. So, what is the third derivative then?
2x to the negative
2. 2x to the negative 2. Derivative of 2 is 0. The derivative of a negative 2x to the negative 1. Negative 1 times negative 2 is positive 2. X to the negative 2. So that is 2 over x squared. Okay? By the way, we haven't really worked with the third derivative or fourth derivative or fifth derivative. If I wanted to keep going, you don't keep putting primes, okay? We quit after 3 primes. If I wanted the fourth derivative, I would write it like this. F, and I'd put a little 4 in parentheses. That is not an exponent. That's telling me I want the fourth derivative. So then it would be a negative 4x to the negative third, or a negative 4 over x cubed. Okay? And you could keep going as far as you wanted. Okay?
Someone actually just did all the tick marks.
Yeah. Yeah, would you cross the fifth one, or, no? We just use numbers at this point. Okay? We put it in parentheses, I think, just to try to differentiate in our head from an exponent. This is a derivative. Okay? That make sense? All right.